Welcome to today's webinar, everyone. The name of the webinar is Let's Get Flexible. My name is Brittany Wegman, and I will be your moderator for today. Before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. First off, if you're unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat and we'll do our best to resolve any issues. Everyone's line is currently muted and will remain so for the duration of the webinar. This will be an interactive webinar with a few poll questions popping up throughout the presentation. If you have any questions throughout the webinar, please type them in the questions panel as they come up. We will have representatives ready to answer your questions directly through the webinar. This webinar will be recorded and posted on the EMA resource page. Once this is posted, we'll send everyone who has registered for today's webinar an email with a link to the recording in the next couple of days. That being said, I want to thank you all for joining us for today's webinar and introduce you to our presenter, Janine Flagg. With over 20 years of experience in design flow and PCB training, Janine is a highly dedicated applications engineer for EMA design automation. She'll start off the webinar with an overview of flex design and some common examples, followed by a brief demonstration. Assuming we have time at the end, we will field some questions in a formal Q&A. So thank you for your attention, and now over to you, Janine.
Thanks, Brittany. So, hello and welcome to today's webinar, Let's Get Flexible, presented by EMA. As Brittany said, my name is Janine Flagg. I'm a field applications engineer here at EMA, and I'll be presenting today's webinar. So, EMA, a Cadence Solutions provider, is a full-service provider of EDA solutions, including software tools and consulting services. The focus of today's webinar is to introduce you to flex and rigid flex design. I'll give you an overview of flex circuits, including some of the terms used, materials required, interlayer constraints, component placement and routing guidelines, and 3D and manufacturing considerations. I will also demonstrate some of the functionality required in a tool when designing flex and rigid flex printed circuit boards. So why flex or rigid flex design? There are two main considerations for choosing flex or rigid flex design over alternate solutions. The number one consideration is packaging requirements, where the finished product needs to be smaller and lighter than would be possible with a rigid circuit design. The number two consideration is reliability. There's a substantial improvement in the shock and vibration performance of flex and rigid flex PCBs. The capabilities of flex designs are much greater than other solutions that are available, such as cable harnesses, discrete wires, and mating connectors. Alternate solutions may offer cost savings, but cannot achieve the high package density or the reliability and performance of a flex or rigid flex design. Flexible or flex circuit technology is used for assembling electronic circuits by mounting devices on flexible plastic substrates, such as polyimide or transparent conductive polyester film. These circuits are flexible in nature and are used in consumer products as well as in computing applications and military equipment. The very nature of a flexible circuit is the ability to bend and flex. This makes it as much of a mechanical device as an electrical one. There are several types of flex circuits. Single-layer flex circuits are mounted on a single conductor layer made of metal or conductive polymer over a flexible dielectric film. Double-layer flex circuits are placed on two conductor layers. Multi-layer flex circuits span 3 or more layers of conductors. These layers may not be continuously laminated together throughout the structure and may even have openings or cavities if needed. The rigid flex structure is a combination of flex circuits placed on rigid as well as flexible substrates. These are then laminated together into a single structure. In 2013, the percentage of rigid flex boards being designed was only about 5% of the overall PCB market. By 2017, the percentage of rigid flex designs more than doubled to over 11%. Rigid flex PCBs show the highest growth rate, reflecting the move towards smaller, higher performance electronics. Here's an example of a product designed using flex circuitry. It's a handheld camera that takes both 2D and 3D movies. Putting this much functionality into a device this small would not be possible without flex technology. And here are examples of rigid flex applications. The Cassini mission to Saturn employed Pioneer's 6 to 12 layer rigid flex boards. Cassini launched in October of 1997. Its probe was equipped with 6 instruments to study Saturn's largest moon, Titan. It landed on Titan's surface on January 14, 2005. Flex is a valuable technology in high shock and vibration, such as during the launch of a spacecraft. There are a few new terms you'll hear when working with flex circuits. A flex circuit cover lay is used to encapsulate and protect the external circuitry of the flex circuit board. A cover lay serves the same function as the solder mask that's used on a rigid printed circuit board. The difference with the cover lay is the added element of flexibility and durability it provides to the flex circuit board. The typical cover lay thickness is 1 mil of polyamide and 1 mil of adhesive. Stiffeners are typically used to reinforce specific areas of flexible circuitry for component support, durability, and mounting. They can also be used for strain relief and heat dissipation. Bonding materials include pressure-sensitive adhesives, or PSAs, and temperature-sensitive adhesive, TSA. A bend area is an area on the board where a bend may occur, and therefore where putting components and vias is not allowed. Even a very modest bend can be an issue if the radius is small enough to put stress on solder joint or plated via. Design guidelines spell out some recommendations when components need to be near a flex, bend, or crease area. A wide variety of materials can be used to manufacture flexible circuits, such as films, foils, and adhesives, with polyester and polyamide being favorites. There's a broad range of adhesives and many types of metal foils that can be used as well. The choice of material depends on how and where the circuit will be assembled and used. Careful evaluation of the various materials and consultation with your fabricator is required to make the best choice for a given application. Now let's talk about component placement requirements on the various rigid and flex areas or zones of the board. Intelligent component placement is the ability to place a component in either a rigid or a flex area and have it automatically placed on the topmost component layer in that zone. 3D collision detection is the ability to check the clearance between components on a flex or rigid flex circuit when it's in its bent or folded state. This type of checking is essential for these types of designs. Flex designers not only face challenges similar to those of rigid PCB designers, but also many additional challenges. The very nature of a flex circuit and its ability to bend and flex means that it will also have a special set of requirements unique to flex circuitry. Here are some of the considerations and features required when routing flex or rigid flex design. Routing arced corners, multi-line routing, contour routing, slide functionality or arc editing, converting corners to arcs, layer structures, and bend areas. Routing arced corners is the ability to route traces that have curved corners instead of orthogonal or 45-degree corners. Since flex designs require that bus lines be routed using curved traces, routing with arcs is needed. Multi-line routing is the ability to route a group of evenly spaced nets side by side in a straight or arced pattern. This is a much needed feature when routing flex circuits. Contour routing allows the designer to route a net or group of nets while adhering to the contour of the board outline. This is needed when routing a group of nets along a complex flex design outline with multiple curves. Slide functionality for arc editing is an important feature when designing flex circuits, as once arc traces are placed or routed, the designer must have the ability to slide them if need be. Without this functionality, the only option would be to completely unroute and reroute the nets. Converting corners to arcs automatically is also necessary when dealing with flex designs. Again, without this functionality, the designer would need to completely unroute and reroute the nets. The layer structure or cross-section of a flex or rigid flex design, like all designs, is set up per the design requirements. In the case of rigid flex design, not all routing layers exist in every area or zone of the board. Generally, the flex areas have fewer routing layers than the rigid areas. For this reason, the tools need to be smart enough to disallow routing in areas where the layer does not actually exist. Special consideration is required for bend areas and across the bend lines of a flexible circuit. To reduce stress, traces need to cross the bend area perpendicular to the bend line, and traces on adjacent layers should be offset to avoid the I-beam effect. The designer must have the ability to set spacing and overlap constraints between objects on different layers. As an example, component pins and vias placed within or too close to the bend area should receive a DRC flag. All pads, including surface mount and through hole, should have tie downs, also called anchoring spurs or rabbit ears. This prevents separation between the copper and the base material. Also, all pads should have fillets, as fillets reduce stress points and help prevent breaking and cracking during flexing. Ground planes or shielding is required to block unwanted electronic interference or noise. If electrical considerations allow, ground areas of a flex circuit should be crosshatched. If design planes are only used as a return path for slower signals or for noise control, crosshatching can be used very effectively. Crosshatching helps to reduce the weight and improve circuit flexibility and prevent tearing. Typically, the bend area and flex radius will be defined by the mechanical requirements. Therefore, it's important to maintain communication between MCAD and ECAD. Bidirectional data sharing of the flex bend information is crucial for keeping both sides up to date. Design tools need to be able to analyze a flex circuit's ability to fit within the space defined and check the clearance between components once it's in its flex state. Ideally, these checks can be done by the PCB designer. If possible, these checks should be done during the bend as well as at the completed bend state. Flex designs require additional checking different from those of rigid boards. These constraints will check the clearance between objects on different layers of the design, such as bend area to stiffener, bend areas to pads, bend areas to vias, and cover lay to pads. Using an intelligent interchange format such as IPC 2581 will enable your manufacturer to more closely capture your design intent. It's best to engage your manufacturer as early in the design cycle as possible. So just to summarize, the benefits of flex and rigid flex design are reduced space, improved signal quality, improved durability, and reduced assembly costs. The main challenges are increased design complexity, increased manufacturing complexity, and higher initial board costs. It's now time for the demo portion of the webinar. Okay, so I have a flex board here, it's actually rigid flex. So we have some areas that are rigid, some that are flex, and the stack up in these different areas is different. And so we actually need to set up different requirements for those areas. We need to define the areas. We need to define the stack up in those areas, and we can also define special constraints and placement requirements. So I'm going to start out by going into the cross-section editor. Okay, and you'll notice that we actually have several different cross-sections. So we have a primary, and the primary is really there to contain all of the layers that are specified. Then we have a flex 1, flex 2, flex 3, flex 4, and rigid 1. So I'm going to add one more rigid. So I'm going to add a rigid 2. And when I add it, I could select all layers in the stack up and have it just put everything in there. And then I could go through and delete some I don't want. I could have it exclude all, and then I can go through and add whatever I want. Or I can copy an existing stack up that's similar and add or delete whatever I need, depending on my needs. So I'm going to exclude all of the layers, and I'm just going to go pick exactly what I need to add. So if we scroll over, we see that my rigid 2 is pretty empty. So I'm going to go in and add, I want to add a paste mask layer, since it's rigid, and a solder mask layer. I want my top layer to be available. I need a dielectric layer in between that and my next internal layer. And then another dielectric layer. I don't need any of the flex layers in this area. I need my next internal layer, a dielectric, the bottom, paste mask, and solder mask. So by the way, you can also go in and I can edit the stack up order. I can edit the order of my mask layers if I want as well. So as an example, in the top, I have paste mask on the outer, I have paste mask as outermost and then solder mask. Whereas on the bottom, it's opposite. So I could take my paste mask and simply move it. Okay, so I've created that. As we do that, you can actually go in and look at your different stack ups. So here's my rigid 2. So it's not using these layers right here, but these are the layers that it's using. You can also see what type of via structures you have available for some of the stack ups. Okay, so we're done here. I'm going to go ahead and create a region in here. This is where I'm going to use my rigid 2. So these ones are already defined. Okay. So to do that, I'm going to go into Setup, Zones, and Create. So over here in my Options tab, I can specify, so I'm going to call it Zone 1. I'm going to specify that I want to use my rigid 2 stack up in that area, and then I can simply draw it. And I don't need to be really picky because it's going to adhere to the board outline and it's not going to overlap an existing zone. Okay. So if I want to go in and change things about this, I can go back in and go into my zone manager. Okay. So besides being a zone for stack up, the zone, so which is zone 1, it's rigid 2. The start layer is top, the end layer is bottom. Okay. I actually am going to make this a constraint area. So I have a special constraint set that I can apply to that. So, and I don't have to draw this 3 different times, one for a zone, one for a constraint region, and one for a room. I can just simply use the same outline. Okay. So I'm going to assign the room as rigid 2. That means that these components are assigned to be in this room. Okay. So once I've done that, let's get into placement application mode. I can see that I have some unplaced components. Now, if I take a component and I place it in this area, it knows that the top layer is the placement layer for this particular zone, okay, because it's available. Now, if I take this and move it to a different area, so this is flex, we can look at the visibility tab, and you'll see that it's actually placed on flex 1. Okay, so flex 1 is the topmost placement layer in that zone. And again, doesn't really fit here, but that's okay. The topmost layer in this particular zone is this is a rigid zone, but its topmost layer is internal 1 for the entire board. Okay, so I'm just going to go back and place it there. So that's what we call intelligent placement. So it understands what layer it needs to place components on based on the zone you place the component in. Okay. So another thing that we talked about was crosshatch shapes. So I'm going to go into my shape application mode, and I'm going to go ahead and create a polygonal shape. Okay. I'm going to place it on because I'm placing it in this flex area. So the flex layer, I'm going to place it on the top flex layer. It's going to be dynamic crosshatch, okay, and it's going to be assigned to ground. So I can start defining it. Again, I don't have to be super careful about how I draw it because it's going to adhere to the route key bin, which is already defined. I'm just going to say done, and it will close. Okay. So now we can actually change this this crosshatch to pretty much anything we want to. If I select this and go into the parameters for this particular shape, I can say, you know, I'd rather have 15 mil hatches with 15 mil spacing, and I want 45-degree angles. And in the other direction, same thing, 15 mil and 135. And it will automatically make the border width the same width as my hatch unless I change it. Okay, so I can go ahead and apply these changes. Okay, so you can see, and you can see that it's attached to ground because it will tell you. Okay, so now if I go over here and I move some of these components here into here, you'll see that it automatically clears around it because it's dynamic crosshatch and also connects when necessary. Okay. So next, I'm going to show you a little bit of routing using arc traces and contour. Okay. So I'm going to get into route mode. I'm going to select these nets. I'm using my contour, okay, enhanced contour. So I'm going to select, this is actually the route key bin, okay, and I want to be 5 mils away from the route key bin. This is basically what I am. So as I route, you can see that it actually contours right around the board outline. I mean, I could contour around every single bend if I wanted to. So, and once I click, now I'm going orthogonally again. Okay. So it makes it very easy to route them equally spaced and following the board outline. So once we've routed them, you need to be able to slide them. So since these are true arcs, we can actually go in and we can slide the arcs a little bit, okay? So that makes it very easy to modify them if you need to, or if you need to move, you know, put something else in. However, if you need to, let's go and go back to our our other design. So let's say we have, this is our other design further along the design path. But let's say we've routed all these traces around here. And now we need to add one more. Okay, so the easiest way to do this, we'll just get into route mode. And again, we're in our contour mode. So I need to pick a trace that I want to contour around. It's going to be this one. So I'm selecting this trace. So it's going to tightly follow that one. And as you can see, it can actually push the other traces. Okay. So I can change back to line if I want to complete this connection. Okay. So you can switch back and forth between arc traces and using lines, 45-degree angles, 90, whatever as you need. So, and if I wanted to go in at this time and make any adjustments here, let's say I want to even out some of this, I can do that. I can actually move these even though there's arcs at both ends. Okay. So editing and sliding with arcs is actually very easy in this tool. Okay. And then, so we talked a little bit about being able to check between elements that are on different layers. Okay, so here's a very good example. We have a transition area and we have tin plating. Okay, we want them to overlap a specific distance. So we're going to go in and we're going to set up a constraint. Let's go into the constraint manager. And this is the interlayer spacing. So this is in the spacing domain and we're using interlayers. And I'm going to just filter for some of the things, for the layers that I need. So I want the transition zone layer, and I'm just going to use tin. And so I want to create a constraint between the transition zone and tin plate bottom. Okay, so I'm going to select that. Once I do that, it places this constraint down here. And now I can go in and define it. So between the transition zone and the tin plate bottom, I actually want an overlap. Okay, so we can have different types of checking. You can have overlaps, you can insist on gaps, you can insist on, let's say in the cover lay, you want the cover lay off of the pad, you want the cover lay around the pad. Okay, so that's an inside type of constraint. I want these to overlap by 25 mils. I'm going to enable it, and then I'm going to assign a DRC label. So the first DRC label for an interlayer DRC is always going to be I. So in this case, if it's an overlap, I'm using an O. So if I have a DRC, you'll see IO. And I want the DRC marker to be placed on the interlayer DRC marker layer. Okay, and I'm going to give it a description. I'm just going to say it prevents tin plate peeling. There we go. Okay, so we have our constraint. We can close out of the constraint manager. Let's see, and one thing that we have to do is we're going to go into our status, and I'm going to update my DRC. Since we created a brand new DRC, we need to update the DRC. And you'll see that I actually have a violation here, and it says IO inside my bow tie. If I float my cursor over it, you'll notice that it says it's an interlayer spacing rule, and we want an overlap of 25 mil according to the constraint value, but the actual value is only 10 mil. Okay, so to fix that, it's actually pretty easy. We can go into our shape application mode. We can simply grab the edge of our tin plate, and we can slide it over. Okay, So we've created a DRC and we've fixed a problem. Okay. Next, let's see, or actually last, we're going to talk a little bit about some of our 3D functionality. Okay, so I have a board here, and I'm going to bring it up in the in our 3D viewer. So it's actually more than a viewer now. Okay, let's shrink this down. Okay, and let's wrap these so they're out of my way. We have a little bit bigger area here. Okay, so with both of them open, you can simply go and you can highlight components in here or select a component and it gets highlighted over here in the board. So the same thing if you click on a component here. Let's set my fine filter for and you can select a component here and it highlights over there. So basically it's you can highlight anything back and forth. You can also move and see moves and so forth, but this is a finished design. So another thing that you can do is you can go into our bend application and you can bend your design. So we have bend areas defined and bend lines. So we can bend it part way. We can bend it all the way. Okay, one bend all the way. We could, at this point, go ahead and bend and fold the whole thing up. Okay. So we can move it around where we can see the different angles on it. So you can turn it around basically any way you want. And I'll look at it. Okay, now I'm going to go into my collision detection and I'm going to calculate. And I actually have my minimum spacing at 0. So if it finds any collisions, they're actually touching. Okay, so I can click on the ones that are touching and we can see, yeah, these guys are definitely, they're too close. Okay. So to correct this, you would probably, you could do a couple things, I guess. You could either change your layout, so, or you could, you know, go back to your mechanical guides and see if you can change the radius here on your bend and put them farther apart. Because this other one, if we look here, we turn it around and look, this one right here, this radius is definitely bigger, okay, which then allows for the components not to touch. Okay, where this one's definitely more narrow. So, and that concludes the demo.
Okay, thank you, Janine. It's all very good information. And at this time, I'd like to open up the floor for the Q&A. Please enter any questions you have into the chat now. If we're unable to address your question immediately, we'll be in contact with you after the webinar, just to make sure all your questions will be answered. And we'll start off with the questions with Janine. Is there a way to communicate or receive stackups from your manufacturer?
Yep, you can use IPC 2581. Not sure if people are familiar with that yet, but more and more manufacturers, especially ones that are doing rigid flex and flex, are accepting IPC 2581 information. It's going to replace Gerber ODB++.
Okay. And is it possible to set design rules specific to flex areas in the design?
Yes, I actually kind of showed that a little bit in when I did a constraint region. So a zone where it has a specific stackup can also be a constraint region where you have specific design rules, line width, spacing and so forth in that particular region.
What defines the bend radius in the 3D canvas?
Yeah, so I didn't really show that, but in PCB Editor, when you define your bend area and the actual bend line, you also at the same time define the bend radius. So it's in the there's bend editor that you would bring up, and that's where you define it.
Okay. Is cross-hatching only necessary in areas where there are bends or folds?
You know, it's preferable to use crosshatch in those areas. Usually in rigid boards, you know, we prefer solid.
Okay. What version of PCB Editor are these flex capabilities available in?
17.2.
Okay, that one's easy. What is the maximum frequency response that we can attain?
Oh, actually, that's probably a great question for the next webinar, which is going to be on signal integrity and power integrity and so forth.
Awesome. Guess we'll have to tune in for that one. When viewing the 3D model, how do you rotate the design, and is there a function key needed in conjunction with the mouse cursor?
Yes. Well, what you're going to do is you hold down the shift key and use your middle mouse. And then you can rotate it, move it any way you want to. Use the middle mouse, just rolling the middle mouse roller, and that zooms in or zooms out. You can hold it down and move the picture around. So it's pretty much all controlled with the middle mouse key, but rotating it requires a shift.
Okay. Is there a way to export an MCAD step file with the bends bent?
Okay. So you can export several different things out of the 3D viewer. So you can export a step model. You can export a 2D or 3D PDF. There's all kinds of outputs that you can export. So yes.
Okay, we'll do a couple more questions here. How can I slide two rigid zones closer together? Do you shrink the length of the flex zone between rigid sections, or what?
Yeah, I mean, you would have to modify your board outline if you wanted to have them closer together. You're talking about the length of the flex, not the radius of the flex.
Okay. Are you able to specify a single layer flex design with drills?
With drills. That's interesting. I mean, you could, except that where would you drill to? I mean, PCB Editor will allow you to design almost anything. You just have to, can you fabricate it? But yes, I'm sure you could put a hole in it if you wanted to.
I'll do just one or two more questions here. How can one change a large number of pad stacks to adjust pad sizes depending on region?
You can change specific pad stacks. You can have, what I would probably do though, instead of going in and changing pad stacks, I would probably have an alternate footprint that would be used in that zone that had the correct pad size that you wanted. And in the case of vias, you can assign vias in region rules.
Perfect. And we'll do one last question here. Is the 3D modeling of Flex limited to the full version of PCB Designer, or can it also be done in PCB Designer Standard?
Yeah, the 3D viewer is available with every tier of PCB Editor. You have the right version. It didn't come out with at the very beginning of 17.2. It came out, this version of the 3D viewer came out a little bit later. So just make sure you're up to date on your hot fixes.
Perfect. Thank you, Janine. Looks like we have a bunch of questions still coming in. Unfortunately, we're out of time for today. However, if anyone has questions that were not addressed during the webinar, we'll be following up with you on an individual basis, so all of your questions will be answered. I'll be closing the webinar now, and we'll be sending everyone a recorded version of today's webinar with a slide deck within the next few days. Thank you for taking the time to join us today, and we hope you enjoyed the webinar.
Thanks. Bye-bye.